Hello everyone. Today we'll be demonstrating a simple global offset table hijack and utilizing buffer overflow problem to execute our own shell code. So for that we have a very simple program which consists of allocation of a char pointer to a p and a buffer of 128 bytes, and then this is just a string concatenate simulation wherein we copy the first argument into buffer, advance the pointer p by the length of that buffer, then copy the second one, and finally print out the concatenation of that. So that's a very simple program. So before this we also need to see where our fprintf function will be loaded dynamically when the program executes. So for that we'll make use of an executable called object dump, and we'll look at the address of GOT for this executable. We can see that the library function fprintf will be loaded at the GOT address 498A0.
So instead of loading the actual fprintf program at 080 498A0, we'll be loading our desired functions address in that place, so that
Right.
when fprintf gets invoked, in turn it will invoke our desired program.
Exactly. So to do that, what we intend to do is that since the program takes two arguments, the first argument will be copied to a buffer of 128 bytes and the second argument will be copied to the P. So if we look at the program, if we look at how the stack allocates this one, so first P is allocated followed by 128 bytes for the buffer. So if there is any overflow in the buffer, it overwrites into the space of P, and hence the value of P also gets altered. So to make use of this opportunity, what we do is we create a file called as addr3.pl, wherein we give 128 A's as input followed by a 4 byte address, which is nothing but the address where we want to write our own shell code. And along with this we also have another Perl file. So in this, basically what we're trying to do is, since we know that all the environment variables will be exported and put on the stack whenever a program loads, we make use of that one, and we provide one of the addresses on that slope, or the address of this address of the stack, where it will consist of a lot of NOP operations and followed by the shell code. So this is just a starting address, so that if execution begins at this address, it slides through all the NOP operations and finally hits our shell code and starts executing that. So this is the address that we want to load in this address. So instead of, when somebody calls fprintf, instead of executing the library functions of library function fprintf, it should start executing from this address. So that's the intent of that. Now let us export that value first. So we need to export that. Before that, let's have a look at how we are planning to push our shell code. So this is the slope edge of 20,000 no operations followed by our shell code. So we just export this as one of the environment variables. So now if we look at our environment variable, it will have 20,000 no operations followed by the shell code. That's the expected output. Now let us delve into our program 1.3, and let us put some breakpoints at line numbers 18, 24,
26,
26, and 28. All right, so Let's begin by running this. Our first input is this one, followed by the second input is this one. All right. So as we know, ADDR3.pl consists of 128 bytes of A followed by the address of GOT where fprintf will be loaded with our own shellcode. And the second argument argv of 2 is nothing but the address at which the slope starts, the sled starts, so that any execution which starts from that address starts executing through all the NOPs and finally hits our shellcode and executes the shellcode. Now, before we move on to this, let's just have a look at how our stack is arranged right now. There we go. So our stack pointer is right now here. And if we look at our pointer P, that is located here. So all these bytes until here, I guess, are 128 bytes. And we'll soon be copying Ace, so it will be visually clear that where it starts and where it stops. So right now, as you can see, P, the value of P is nothing but this value, and it is located at 6C. I'll do an N. So now the value of P is getting changed. Now if you look at what is the value of P, we see that it is 8D7C. So that is string length of argv1, argv of 1 plus the buffer. So we know that the string length of this value is 128 bytes plus 4 bytes of address, so that is totally 132 bytes. And the value that generated out of this is 8D70. And let's look at again the same address where the P is supposed to be stored, and let's look at what is the value of P. As we can see, the value of P has changed. It is 8D70 right now. Now, this is the part where all the magic happens, because ideally the buffer is supposed to just store 128 bytes. So it starts writing the 128 bytes from here or here, and it moves on till 128 bytes ideally. But just because we are trying to overflow it with extra 4 bytes, it is going to also overflow and write the last 4 bytes of the value that we gave as argv of 1 into the value of P. So essentially our pointer gets changed to the GOT address. So let's carry out that operation. And now if we are printing the stack again, we should be able to see the GOT address instead of 8D70. There we go. We see that we have successfully created a destination for a new value to be written into an address of 6C, which is the value of P. Now if you look at the value of P, it is nothing but, yeah, now it is directly showing that it is pointing to the fprintf. So if nobody writes onto this address, fprintf will still be safe, and any further operations would still be pointing to the fprintf, and it will be executing the code for fprintf. But now with this next operation, upcoming operation, we are going to copy the slope address that we have where our shell code is present. We are going to copy that one into P, the destination that is within this address. That is, we are going to overwrite whatever is the code for fprintf and replace that with our shell code. So once we do that, now if you are planning to execute fprintf, it should ideally run our own shell code. Before that, we can also have a look at our environment variables, how they are put up on the stack. So we see our environment variable. So the address that we gave as the second parameter is nothing but one of these addresses. These are nothing but nope operations, which would be followed by our shell code if you look at this. So once we give one of these addresses as the next instruction address, it starts executing the instructions, which are all nopes, and finally comes to this place, this address, and starts executing our shell code. So it should ideally now take us to a new shell code. There we go. That's it. Thank you for watching.